Hello again. This is our final video of Chapter 6, Modeling Relationships of Bivariate Data. Again, these are linear correlations. We need to check out to find out first if data is linearly correlated before we try to perform this type of analysis. So then what we do is we find the line of best fit through something behind the scenes. This is the linear regression analysis based on the theory of the sum of the least squares. If any of that doesn't make any sense, just ask for my help and I'll explain it slower and perhaps using different words to help you out with that. Today, we're going to be taking a look at how the big formulas that are associated with this work. And you may recall, you've heard me say, for many of you, you're never going to need to be able to do this, but I think it's worth a bit of time looking at what is happening behind the scenes. And I know that some students will end up using a stats-based topic for their internal assessment. So I don't want to leave this completely alone. I want you to see what's involved, but know sort of in your mind that this might not be something that you'll ever have to do yourself, but I'm going to go ahead and do it anyway. And I'm going to follow up the lesson with one more example of a practice of using our GDC to find the line of best fit using linear regression analysis, and then providing some interpretation, and then analyzing the trustworthiness of that analysis going forward. So here we go. In most cases, you are going to be using a calculator to find R. That's just, there's no two ways about that. You are. Important for application students is to know how to interpret that information and what to do with it once you have it. Doing it sort of quote unquote by hand, it doesn't mean doing every calculation on your own. It just means showing all the steps that go into calculating R. And it's internal assessment students who may end up having to do this. Now, this is just about as intimidating as you're ever going to get. Here's the formula. R is what we call the covariance of SXY divided by a couple of standard deviations as a product down here. Now, the textbooks unfortunately use the S version of standard deviation. Don't worry about that. And how you build these things, you don't even go and get them on your own. Look at this. The SX formula is here, the SY formula is over here, and then the SXY, the covariance, is the one over here. How do we figure all that out? Well, remember when we did the two variable analysis when we had two columns of data on our spreadsheet on the GDC? A lot of the information that I've circled at the bottom of that screen is actually told to you. You don't have to compute them at all. Hopefully you remember that this sigma means the sum. And so we're going to be looking for the sums of various things in our data field. I'm going to put that aside. Now, once you have that information, that value of R, that tells us whether or not, linear regression analysis is a worthwhile type of analysis. But then you'll notice that this is the format for a line where it is a slope and a known point here and here. So we've done that in Chapter 4, and we're doing it again, but the inputs here are very, very, very precise. And once again, covariance and the square of the standard deviation of X. Those are the key ideas. The theory behind that, maybe University of Oaks, but you're not going to see it from me and not here. Okay, now I'm going to go ahead. Just watch this like you're watching a movie. If you want to follow along on your calculator or in pen with paper, that's fine. But again, it's only the students who will ever do an internal assessment using a stats and this variety of statistics, let's be honest, who may ever have to do that. So it says use technology to find the equation of the regression line. Right, we're gonna do it manually, and I'm gonna use this formula to show you how. So I've got a random data field it's not connected to any sort of reality-based topic, no hypothetical like children throwing a discus or anything like that. Families buying groceries. It's just a series of numbers, and I have no idea, nor should you have any idea when you look at a data field like this as to whether or not it's positive or negative regression or positive negative correlation. You don't know, and I don't care. I'm not going to let myself be motivated by what I see, just what I can compute. I'm going to run through these formulas and show you how it's done. So how do you do this? First thing I did was I took that data field, that's that table of values, and I put it in my GDC. Now I've done some screen captures there so it all fit in one screen. And this is not new, so I'm not going to go ahead and show you all the steps. I did a two variable analysis, and there were some key things that I wanted to know. That straight line, it talked about S, X, Y, the covariance, and I had a big formula for how you build it. But you'll notice that there's tons of other stuff like sitting around in here. And these are really useful pieces from my formula. Let me show you how this works. This first formula, SXY, I'm going to work on this one right here. Notice it says first things you need is the sum of all the products of x times y. That means every x value times every y value side by side, and then add them all up as you go through. But that number there is right there. It's told to you. You don't have to go through the table manually and find them. And then it says you want to take the sum of all the x's. Well, they told us that too, and that's why this is 55. The sum of all the y's, they told us that too, is 105, so we don't have to do that manually. The number of data in the set is also told to us, so you don't have to do that. Anyway, and on you go through this whole sort of minefield of formulas adding up. Here is the sum of all the squares of x's given to us, 385. There it is, and on and on. Then I end up with these calculations over here: 158.5, 9.0 whatever, and 18 point roughly 7. What do I do with that information now? It said that the R value was the first one divided by the product of the next two, which gives me this quotient, which leads to this answer here, 0.934. Now that, or 0.935, I suppose, that R value is the R value. That's the Pearson, product moment correlation coefficient. And it tells us how meaningful it is to use linear regression analysis to find a straight line to represent a data field. Notice we still haven't even seen the data presented in a scatter plot. I don't need to. I know that it's correlated very, very high. It's positive, strong correlation. That's all I need to know. Now, if I was to go back to my two variable stats, take a look down here. I've highlighted it in yellow and surrounded it with a red rectangle, 0.93476. There it is. Now, most students will only ever use the GDC to find this value here, and the premium is placed on you knowing what to do with it once you have it. But now you've seen how it's actually calculated. Now we want to work out the actual equation of the line. It's y minus, and x minus a known point. Well, the known point is the mean point. And this value here is the covariance divided by the square of the standard deviation. Work all that out as well. If I take all those pieces together, these pieces are recycled somewhat from the previous slide. You may recall some of these numbers here. And I put them together, and it tells, and I pulled out the mean point from that summary list, put all those pieces into there, and you end up with that. And I've simplified it. So that quotient goes here. The mean of the y's goes there. The mean of the x goes here. I distributed that, brought that over to the other side, simplified the whole thing, and I ended up with that straight line. Now, again, I have still not seen a scatter plot of that data, and I have no idea what it looks like. I do know from my analysis that of the R value that it is a strong positive correlation, and so this form of analysis is appropriate. And I know that that's the line of best fit, so I can already work with this data, and I haven't even seen it. Now, what can I do with this? I went ahead and did the linear regression analysis just to verify. There's that value of R that we had before, and look at this. It says the slope of the line should be 1.9212, ta-da, and the y-intercept should be negative 0.7 roughly, and there it is. So this is what's happening on the GDC, and all that work that you saw, that's what we used to do by hand before we had computers and calculators, and what some of you will need to do for your internal assessment. So now I went ahead and actually made the scatter plot to give you that visual confirmation. Those blue dots in the upper right are in fact a scatter plot of this data that was presented to you. To use technology, but we didn't. We did it long form, but you could use technology. We also did that, I suppose, and there it is. 1.92 x that's the slope, 1.92, and the y-intercept is just a hair under 0. So we've got that down. Okay, so that's all set. As promised, one example I want to guide you through. This is the last example you're going to see. Investigate whether speed cameras have an impact on road safety. So I'm hoping that if the officers or the police department puts out more speed cameras, perhaps that will cause drivers to moderate their behavior, slow down a little bit, and then there won't be as many accidents. That's the presumption. So we've got a big set of data here. I don't even know. That's a lot of different measurements there. But in places where the number of speed cameras were counted up, also the number of car accidents were counted up, And there we go. So we're going to do sort of the regular tour here, and I'll guide you through it step by step. First things first, get the numbers in your GDC. The 16th data point was 19 and 32. And so that's what I have right here, 19 and 32. I don't want to have any problems about missing data, doubling up data by accident, or having them mismatch and don't end at the same place. I went ahead and did a regression analysis, and you've seen for yourself now how much work this command on your calculator is actually saving us. I see that the slope is that, I better first check, R, it's in the safety zone. It's a sufficiently close enough number to 1, in this case -1, to indicate that linear regression analysis is appropriate because that number is strong. But it's strong negative correlation now, meaning the more cameras, the fewer accidents. Now let's take a look at our list here of questions. Construct a scatter diagram. We can do that on the calculator. Calculate the value of R. We've already done that right there. Describe the relationship. I just did that. The increasing number of speed cameras results in a lower number of accidents. Find the regression equation. Well, effectively that's done. It's right there. State and interpret the, here we go. And that's something else that we can do. State and interpret the gradient and y-intercept of the line. Well, the gradient means that's marginal rates, right? So as X increases, and that's the number of cameras increases, that's the quantity change that you're going to have here. So it basically means for every additional 1 camera that you're going to have 1.06 fewer accidents at that location. What does the y-intercept mean? Well, a y-intercept, you may recall, is when a line goes through the y-axis. In other words, the X value is 0. So it says theoretically, if there were no cameras, you would expect there to be 52 accidents. Estimate the number of car accidents in the city with 10 speed cameras. Well, let's go ahead and do that. There's your y-intercept. That's how many accidents you would expect if you had 0 cameras. I went ahead and I traced it, and it said, what if there were 10 speed cameras? So I put 10 in for my X value on a trace, and it told me that the Y value is 41.4. That would be the number of accidents. We'd expect, if we were in charge of police department policy, that if we put 10 speed cameras, we'd expect about 41 accidents according to that data. And that is that. Okay, so there's a whole question. That's exam sort of style and exam worthy. And you've got this left to do now. At the risk of making this a bit longer, I couldn't resist. I wanted to show you one more thing. The 2 sections, G and I. There they are. Some nice questions for you to do. And what I've done is I've made a short video. It's about 2 minutes long, embedded here, which is going to show you that least squares and what your calculator can do. Now, I went ahead and I made a random data field. This data is not supported by any question whatsoever. So watch what happens here. So I put the data in. See how far down it goes. But it's called the X and Y, very bland. And I can see that there's the last data, the 6th entry. So it's a very small data field. You've got 6 X values and 6 Y values, and there's a scatter plot of them. What am I going to do with that? I'm going to go and I'm going to calculate do some stats calculations on that data, see their interconnectedness. And I'm going to go to linear regression. Remember, you always got to check we'll do 2 variable stats first. Let's figure out what this R value is and what the means are. And I can see that the R value, where is it? Down a bit. Oh yeah, the mean of X is 5.5. The mean of Y is 4. And the R value is 0.91. So it's significantly high, close to 1. So it's strong positive correlation. Now, what am I going to do with this information? I'm going to go ahead and find the regression equation. Back to stat calculations. I know that this is an appropriate analysis because the R value is so high, so close to 1. Again, I'll put it in that it's just X and Y. Again, it's saving this to F1, so it's already going to be pre-installed. I can graph it really easily. There's the equation of the line. Oh, there's R. The equation of the line is 0.56 X plus 0.89, and it's stored into F1. I've highlighted that on top. So if I go to a graph page now, I can go here. The first function is going to offer me is F2 to 1F2. Back up you go to F1, pre-installed, hit enter, and the graph is presented to you. Move that label out of the way. Don't like it there. Now, what's the next thing we can do? I put the mean point in there just to verify that the line of best fit does always go through the mean point. Now I went to a stats and data page, and I also made a scatter plot there, and I'll show you how to do that if you want to, but I just want to show you about the least squares here. From here, you can ask for an equation, a regression equation, line of best fit. And there it is. Pull that out of the way a little bit. And the other thing you can do is actually show that least squares. So if I go to analyze the thing, I can go to residuals, and it says to show the residual squares. And there they are, as presented or discussed before. And if you took the area of the 1, 2, 3, 4, 5, 6 little squares, some of them bigger than others, they would add up to 1.099. And the fact is that if you were to adjust the height of that line, that green line, or either up or down, adjust its slope, adjust any aspect of it in any way, tilted, elevated, moved in any manner whatsoever, this number here is going to climb, and it's no longer the least sum of squares. And so that's why that makes this current line that you're looking at the optimal one. And that is the end of this chapter. So you should be working on section G and section I, and that's the end of chapter 6. All right, let's get to work.